Hello everyone, welcome to my YouTube channel. If you're new to the channel, my name is Dennis, a student navigating his way in the world of machine learning. I love to share what I learn in the world of AI, and I would love always to take you along with me by sharing what I learn. In this video, we are going to use something called feature extraction, that is, take two AI models and see how well they perform on a data set of our choice. In this case, the Food101. If this is something that interests you, consider subscribing and let's dive right into it. To begin with, we will go through what the Food101 dataset is all about. So the Food101 dataset, as you can see, has lots of images. We have 101,000 images, and there are 101 food categories. What it means is that we have different food types from chicken curry, chicken wings, fried rice, grilled salmon, hamburger, ice cream, pizza, steak, and it goes on and on and on. And we have 101 of these categories, and there are lots of images. And as you can see here, it is available to the public for free download. For some reasons, we are not going to use the entire dataset. We are just going to take only 10% of this 101,000 images and then train our models on them. We talked about using feature extraction. So with feature extraction, we said we are going to use EfficientNet and ResNet. Now, what is even feature extraction and what are EfficientNet and ResNet? If I move to my TensorFlow, over here on Kaggle Models, these models are also free on Kaggle. This is for EfficientNet, and again for ResNet, ResNet is also free on Kaggle. Let's dive into what ResNet and EfficientNet are. So there is a popular image classification dataset called Imagenet that contains millions of images, as you can see here. Now I'm bombarding you with a lot of stuff. Now this Imagenet dataset contains millions, as I said, millions of images, millions of them. All the links to this will be in the description. Now the ResNet and EfficientNet have been trained on these millions of images. So if you come here to EfficientNet and we scroll down to training, you can see that for image classification, Imagenet. So this EfficientNet has been trained on all the millions of images from Imagenet. The same thing goes for ResNet. ResNet has also been trained. If you move down to training of this ResNet, you can see for image classification, Imagenet. So these two AI models have all already been trained on the millions of images from Imagenet. Now you want to take these AI models that have already been trained and then see how they will perform on a data set that we have chosen, which is also a data set of images, but in this case, a data set of food images. If I am clear, I'll just repeat it again. We have two AI models that have already been trained. Now we want to see how these two AI models will perform on our food dataset. Now, before we actually dive into the project, there are a few libraries and frameworks I would like to introduce you to. So when it comes to machine learning, some of the popular frameworks are TensorFlow and PyTorch. But in this project, we are going to be focusing on using TensorFlow for our implementation. Again, you need to have a certain level of control over the Python programming language, which is very essential if you want to go into the field of machine learning. Another library we'll make use of is Matplotlib. Now, Matplotlib is very helpful when it comes to visualizations. If you want to visualize and see some things in your project, you understand more how we use it when you get into the project itself. But Matplotlib is also very useful. Another thing is called pandas. Now, pandas actually enable us to make tables in our project. Very, very useful library. We also go more into it. And lastly, we are going to go into what we are going to use something we call Google Colab. Now, if you want to follow along with this project, you do not need to make any complicated setups or installations. All you need to do is to go on Google and type Google Colab. If you do this, you will get to this interface. As you can see from the link here, colab.research.google. You get this interface here, and you'll be able to just follow along without any complicated setups or installations, just like that. So we are going to use TensorFlow. Python is the programming language of choice. We are going to use Matplotlib for visualizations, pandas for making tables, and then Google Colab to make the entire project. One big reason why we use Google Colab is also that it is free. You don't need to make any installations or any complicated setup, and it also comes with a free GPU. It has limitations though, but it is very, very good. So if you see here, if I come to connect and I come to change runtime type, I have a CPU and a GPU. A CPU makes training of your models very, very slow, but with a GPU, it's very, very fast. Now, it's slow depending on your data set, but then GPUs are known to be very fast when it comes to training AI models. So this comes with Google Colab for free, which is one main reason why we actually use Google Colab. Enough of talking, let's get right into it. So first things first, let's connect our GPU, change runtime type, and let's take GPU. So I change from CPU to GPU, and then I click on save. Right. So let's check what time it is. Import date time, and let's say print, and I ask for the last run of this notebook is, I say date time dot now. Great. So I'm going to run this. Now to run the notebook, all you have to do is you're going to use shift plus enter to run to the next cell. So shift plus enter, and you can see that my cell is currently running. Now it is not just running, you can see it's also connecting my GPU from here. So you can see my GPU is connected. So the last run of this notebook is today's date and today's time. Right, so now it is that our GPU is connected, but let's actually check whether it's connected. To check whether your GPU is connected, you use the bash command, which is exclamation mark, then you type nvidia-smi, then again shift plus enter. Great. So you can see that we indeed have our GPU connected. So now that we know today's date, which is actually not necessary, and we know that our GPU is connected, we have our GPU ready. The first thing we have to do is to get our data, right? We need to get the data. If we want to train on the data, we need to get this data, and we know how to get it by downloading it. So we are going to use some few commands down here to get that. So I'm going to do webget bash webget, and then I'm going to pull a link that I have already in there to get a link. So let me put a comment up here and say get the data and get here, right? And I'm going to write shift and enter to download the data. Remember I said before that we are not going to use the entire Food101 dataset. We are just taking 10% of the dataset, and then we will use that. In a later video, we'll go into using the entire dataset, but now we want to make things very simple by using only 10% of the dataset. So the link that I pull, I'm going to put everything in the description all the links for downloading this. So as you can see, we can see that it is 100%. That means the data set has been downloaded. But to check whether it's been downloaded again, we need to do a bash command, which is, now because we are using Google Colab, if you want to do any command like in your terminal or in the bash, you always have to begin with the exclamation mark, okay? And then we do ls. You know, if it was in your terminal, you would just type ls. But because you're using Google Colab, you need to let Google Colab know that this is a bash command. ls, and then either you do command enter or shift enter. So I mostly do shift enter, so shift enter. Great. So you can see that we now have 10 food classes 10%.zip. So it means that the food classes or the Food101 dataset has been downloaded. We have 10% of it. So if I go to my folders here to actually see it, you can see that I have it downloaded. But there is a slight problem. It looks like we downloaded it as a zip file. So in order to get the actual data, we need to unzip this to get the data that we actually want. So that is what we are going to do next. We are going to unzip this zip file. Again, to do that, we are going to, so let me put it here. We unzip the file. To unzip the file in Python, we can do import zip file. Great. And then with zip file, we can now unzip the file that we have currently, which is, quite simple. So let's do that. I'm going to say with zip file dot zip file. See, we have that here. And then we put in a string, and I put this name here, which is 10 food classes. I can just copy everything here and put it inside here. And again, we want to read this file. I say as zip ref. Now I'm going to take this zip ref and say extract all. So we are going to unzip this zip file. We are going to extract all the files from this zip file. So again, shift plus enter. Great. Now how do we know whether the files have actually been all extracted? To do that, again, bash ls or exclamation ls. We want to see. Great. So you can see that we have the zip file down here, and then also we have on top of it 10 food classes 10%. So if I go here to actually confirm it, you can see that we have 10 food classes 10%. Now we can actually inspect it here by just doing this, clicking on it here. We have some test images and we have some train images. But to make it more professional, let's do this inside. Let's write some Python code to do that. Or let's do this here now, and after we will write some Python code to also do the same thing. So I can go to the test images, or let's start with the train images. We go to the train images. Okay, we have 10 classes. So in the original Food101 category, there were 101 food categories, but we are only taking 10 of the 101 food categories, only 10 of them. And then we have separated them into training and test data. So here the training images were 750. If you go back to, and also their testing images were 250. So they had these total number of images, and then for each class, they had 250 for testing and then 750 for training. This might get confusing, but don't worry, we'll go more into it. So 250 for testing and then 750 for training. If you go back to our Colab, we also have 10 food classes under the train. So inside the chicken curry, if I click on it like this, you see we have all chicken curry images. images of chicken curry, different types of chicken curry, right? If I close it, the same thing for chicken wings. We have all kinds of images of chicken wings. I'm going to close it here. Now, if you come to the test also, we have 10 classes as we said before, and then all kinds of images of chicken curry for testing. All right. So you can also play with it if you are following along and see how the images are. Now, next up is let's do all of this in our Colab. So I'm going to close it over here and then come back and write some code. So to do that, we call it walk, okay? You're going to walk through the file. So to do that, let's say, let's walk through the folder. We have created this folder here. We unzip this and we got this folder. So now we want to walk through the folder to know all the items inside the folder, the number of images inside of it, the classes inside of it, the number of folders even inside. We want to know everything about this folder. So we're going to take a walk inside the folder. So let's take a walk. To take a walk, we have to import OS, which is the operating system that we are on. And then we see for a for loop for the path of the directory, for the name of the directory, and then the file name in os.walk. In our walk, you see we are taking a walk. Now where are we taking the walk? We need to pass in the path of that folder, which is this. So I can just copy it and then paste it in here. Then I can come back to the end, put a colon, and then I'm going to do some printing. I want to know what is going on. So I'll say print, and I'll put an F formatted print. So I'll say there are this, and then I'll count the number of folder names or the directory names. So length of the directory name. So there are, let's say 2, and I'll say directories, or yeah, there are this number of directories and this number of file names. Now with the file names, I'm going to make it images since we are dealing with images, and I'll put the directory path. Don't worry, as you go along, you understand how to write some of this code even by yourself. So to explain what we are doing here, we have a for loop that is walking through this directory or this path we have here, the folder we created. Now we want to know the path of each folder or file inside this folder, their names and their number. We want to count them. So I'm going to run this. I think it would be best if you see it for yourself. So it says that you are connected to a GPU runtime, but not utilizing the GPU. Yeah, it comes sometimes. So we have some information here. It says that there are 2 directories and 0 images in 10 food classes 10%. So you can confirm that here. We have 10 food classes 10%, and it says that there are 2 directories. So if I open it here, how many directories do we have? We have 2. Great. Do you have images there? No. So 0 images. That's perfect, right? Again, it says that there are, I think there was a grammatical error here. There are, okay. And let me rerun it. Great. So you see that there are 10 directories and 0 images in 10 food classes percent 10% / train. So you see that if I go to my train directory here, there are 10 directories, and that is true. We have 10 classes here. 1, 2, 3, 4, 5, 6, up to 10 classes, and then we have 0 images, which is also correct, right? In that directory link. Now if you go to the fried rice inside the train, if I open fried rice inside the train here, it says that there are 0 directories, there are no folders inside fried rice, and there are 75 images. So you can see they have these files. There are 75 files inside here, inside the fried rice. So you can see that it goes the same for all the other directories inside the train. We have 75 images for all of them. So I can close it. So inside this train, all the folders in here have 75 images inside them. So we have 75 images of pizza, of ice cream, of hamburger, of grilled salmon that we are going to train our model on. If I close it and I come back to the test, so you can see we have 10 directories and 0 images in the test folder. So if I come to the test folder as well, you can see that that is true. We have 10 directories. Now, the number of images that in this test directory is quite different. So again, if we try the fried rice, if you go to fried rice, it says that for the fried rice, we have 250 images. So we have 250 files inside the fried rice, which we'll be using for testing. Now, naturally, we always have more train images than test images. But because we are doing feature extraction, that is why we have lesser training images and more test images. As we go along, you understand it well. So we have taken a walk inside our folder to know the number of images we have in there and the number of directories. It is clear that we are dealing with 10 food classes, right? But it's too easy to just talk about it. We have 10 food classes. It's too easy to talk about it. Let's write some code to actually see these food classes we are talking about. So I'm going to close it here. And then let's write some code. So we know that the test directory. So let's first do something. Let's set test and train directories. So we can do train directory equals. So let's come to the top here. Where is our train directory? This is the path to our train directory. 10 food classes, 10% train. That is the directory path. That is the folder that contains all our train images. So we can copy it here. Yeah, we do some more copying. And then we give it as a string. So we do that and then we paste it. So this is where our train images are. And we can do the same thing for our test directory. So text directory, and then we can look for where our test directory is, which is there. So we copy that as well. And then we paste it here. Wonderful. So now we have the directory that contains our test images and a directory that contains our train images, which is actually true. 10 full classes percent. And then when I open it, I have test and I have train, just as we have over here. Perfecto correcto. Now let's get these class names, these names that we have. Let's try to, get them. But let's write some code. We can't just look at them here. Let's write some code to actually get our class names. So get class names. To get our class names, we are going to import pathlib. And then let's create a new data directory. So I'll explain this as we go along. So data directory, and we say pathlib.path. Now what path do we want to take? Now this is two-way. Now if you go to our train directory, we have 10 classes, right? And when we go to the test directory, we have the same thing, like the same classes, the same 10 classes. So with the path, you can actually choose either the train directory, you will be right, and when you choose the test directory also, you'll be right. Because again, if you go in there and you check, they have the same class names. The names are all the same. There are 10 of them, the same class names. And when I go to the train, again, I have the same class names. So whichever directory you choose, you are right. So in my case, I'm going to use the path to be the train directory. Whichever directory you choose, you are right. Great. So I'm going to get my class names. So I'm going inside this directory, which is the train directory here. So I'm going to enter the train directory, this train directory, and filter and get all these names here. These names, I'm going to get all of these names. So to get them, I'm going to store them in a variable called class names. And I'm going to say sorted. I want them sorted before I even store them. And I say item dot name for item in data directory. This data directory here. Dot say glob. You should go through this data directory. You should go through every item inside this data directory. So this here is a wildcard, the asterisk, that go through this data directory, which is the train. Go through all of them, and for each item, grab the item's name. Okay, grab the name, sort them, and then store it in this name here called class names. So we can do this and say class names. If you want to see the class names, and again, if you remember how we get how we run the cells, we can either use command and enter or shift and enter, and this still work. So we do that. Looks like we have an error. It says that train directory is not defined. So what this means is that we did not run the cell. Okay, so always make sure you run your cells before you move to the next. So I'm going to run this cell here. Now we are going to rerun this cell again. Wonderful. So you can see that we had an error that the folder we were trying to access was not defined. But after we run it and we rerun, we were able to get all the names. So now we have all our class names. We have them stored in a list. We have chicken curry, chicken wings, fried rice, grilled salmon, hamburger, ice cream, pizza, ramen stick, sushi. So again, if you go there and then you check, you'll see that we have all these names there. Or if you tried the train also, you can see we have all these names there. Now we have the class name stored in a list. Wonderful. So the next thing we can do now is that, if you remember during the beginning of the video, I told you that one thing that really helps us to visualize is a library called Matplotlib. Now we said that inside these folders, we have images in there. You see, if I go to chicken curry, we said we have some images in there. But then it's not enough to just say we have images in there. We have to see the images. I'm somebody who believes in seeing is believing. I want to see stuff before I believe. So we want to see these images, that it is indeed chicken curry that is inside these folders before I can believe that yes, they are indeed images. The same thing goes for fried rice. The same thing goes for all these classes. I want to see that they are indeed images of pizza, images of hamburger, images of ramen, images of sushi. I want to see these images before I will believe that they are indeed images of these classes. So to do that, we are going to write again some more code, which we say that view sample images. So let me close this thing here and write a comment. We want to view a sample of the images. Now we're going to do this randomly. So I'm going to import random, and then I'm also going to import what I told you before, matplotlib. Import matplotlib.pyplot. So pyplot, Python plot. Okay, I'm going to use it as a PLT. I'm going to give it an alias PLT. So with these classes, I'm going to randomly choose any class. Okay, so I'm going to say random class equals, now say random.choice. As I said before, you need to have some level of control on the Python programming language. So this is going to choose any of these class names at random. We can test it to see. So random class, if I run the command plus enter, you can see now we have steak. If I run it again, we have ice cream. So it is just choosing them at random. Okay, they are just at random. So we know that we have a random class. So now that we have a random class, now let's choose a random image from the random classes. So we say random image equals random.sample. We're taking a sample from that. and we are going to see os.list directory. Now we have to pass in the path to this list directory. I'll explain it as I type it, so just don't worry if in case you don't understand it. So train directory, the directory we have train directory plus the random class, okay, and then I'll pass a value 1 over here. So the reason why I'm passing this value 1 is I'm using a sample. Now in Python, if you go to the Python documentation and you read about sample, so let's actually open Python here, Python documentation. Okay, so if you go to the Python documentation and then you search for random.sample. Okay, so we have random.sample here. So random.sample, you have to pass in a population, okay, and then you have to pass in the number of the population you want. So for instance, the population here can be a list of values, and then the k will be the number you are picking from the population. So they give an example here that I have a sample that's a list of red and blue, and also there's another one counts 4 and 2, and I have a k value of 5. So with a sample, I'm choosing the values. No, let me get a better example. I think so. Let me explain it better now. You have a sample. So in the sample, you have a list of items, and the k value is that out of the list of items, you want to pick a value out of it. You want to pick some number of values, the k number of values out of it without replacement. So you cannot repeat. You cannot pick red, red, or you cannot pick blue, blue. This is why the sample is very important. So you are picking them distinctively. But when we're using the random.choice, with this random.choice that we use over here, you can see that we can choose the class names again. You can repeat the class names. But random.sample, once you choose one class name, you can't choose it again. So this os.list directory is going to give us a list. It's going to give us a list of the items inside this path we have passed. So the path we have passed is that train directory. So we are going to, let's visualize it. We are going to this directory and we said train directory. So train is here. Now we said train directory plus random class. So the random class could be any of these classes. Let's say chicken curry. Okay. So we have all these. So the random sample is going to put all of these items in a list. So we have all these images in a list. Now we are saying that the k value here is equal to 1. So out of all these images, out of all the over 170 images we have here, we want to pick just one image to view. We want to see just, you should pick only one image to view. Okay, so we have a list of the images. We want to pick only one of the image, only one. Great. I hope it was clear. So the next thing we want to do is that we want to view it. To view it, we need to use something in the matplot, also called import matplot lib.image as mp image. I think sometimes I talk a lot. all right. So let's give it an image. So let's say image is equal to, we want to view the image. We took one sample from the images as a random image. Now we want to view the image. So to do that, we do mp the image, the matplotlib image dot image read. We want to read the image, but here we need to pass in the path. As you can see, f string, we have the string here. We have to pass in the path where the image is. So to do that, we're going to say image path, but we have not defined what this image path is, so we have to define it up here. So image path equals the train. We are going to this train directory, this path, we are passing in this path, image train directory plus random class, right? Random class plus, and then we do this here plus, because it's a directory, So we moved to the random class. Now we want to use the random image. Now we add a 0 to it. We add this 0 to it because this random image that was returned, it was a list. It was a list of images, but only one image. So I can actually comment this out and then show you what random image is. Okay, so it says that no such file or directory, 10%. Great. So what it's saying is that we need to, the path that we passed here is not correct. It says that 10% train. Now you can see that there is no slash in between here. It has combined the ice cream, the class, to the train, right? So let's correct that. Let's go back to this place and then let's add a slash here and a slash here and rerun it. Okay, very important. So now we can rerun this file again. Great. So you can see that we have a list that has the image inside it. We chose out of the plenty images this image at random. So what we are doing is that we want the path to where this image is located. Where is it located? It's in the train directory plus the random class, the class we chose as random, slash where the image is, that random image is. And then we pass that image to the IamRead to convert it to a NumPy array, and then we can get the image before we can show the image. A lot of talking, but let's get it done. So I'm going to uncomment this again. So yeah, we have it done here. So we are able to pass this value here. So the reason why we have this 0 here is that we want to access the item in the list. You can see that this is a list, but you can't pass a list to this. This here is a string. You can see it's a string value here. You can attach a list to a string. So what you have to do is that you want the item that is inside the list, which is this string here. There's a string inside. So you add a 0 so you can get the item that is inside the list, and you attach it to this path. That is where this image is located. And then you put it inside the IamRead to convert it into a NumPy array before we can actually visualize it. So we can actually continue from there. So to show it, you have to use the PLT. Like we want to plot the image, right? We have the image now. So we say image show and then img. Wonderful. So let's run it now and then we can modify it along the way. Great. So you can see we have some axes around it and we have some stuff on top, and we don't know what this is. This looks like I don't know, it looks like something, I don't know. So let's modify the code and let's see how it goes. So we can see PLT, let's give it a title, and the title is going to be the name of the class, the random class that we choose, so that we know what kind of image it is. Then the axis looks ugly, so you have to put away the axis. So PLT axis, let's put it to false. We don't want to see any axis. And lastly, no, let's run it again to see something first. Oh, wonderful. So this here is sushi and the axis is gone. Wonderful. But let's add something else. Let's add PLT. No, let's print the shape. So print the shape of the image. So image shape. Let's say img.shape, the shape of the image. Now you can see we have some information on top here. We don't want to see that. So to remove it, you have to add a semicolon here to remove it. Okay, and then we run it again. Wonderful. So we have here chicken wings. Chicken wings. Wow, I feel hungry right now. And it has the shape of 512 and 512, right? Chicken wings. So we can run it again to see other images. So if you want to run it again, command enter. Wow, we have pizza. Okay, you can see the images have different shapes. 262, 512. Okay, different shapes. 512. This one is what? Ice cream. Ah, sushi. Okay, chicken wings. Nice. I think I need to get myself some chicken. We have some steak. We have some grilled salmon. Ice cream. Oh wow. So it looks like indeed we truly have images inside our folder. So we want to see these images, which of the models, EfficientNet and ResNet, which of these two models will be able to indeed tell us that this image is an image of chicken wings. This image is an image of salmon. This image is an image of ramen, yeah, an image of pizza. Which one will really do well to tell us what image this actually is? Which one of them? So to do that, we have images separated into training and tests, right? So we are going to use a portion of the images to train these models again, and we're going to use the portion of the images to do the testing, to test it to see, can you really let us know what image this is? Can you really let us know what image that is? Okay, so you can see that we really have some images here. I can keep running them. Different images, right? This is so wonderful. This is one main reason why I love machine learning. All right. So next up is that we have to get our train data. We know where the train data is. We know where the train directory is. We know where the text directory is. We know where they are. Test entry, we know where they are. But we need to grab the train data and we need to grab the test data so that we can use them to train and test and also build our model. So to do that, let's go down here and then let's write some code. So get the train and test data and reshape them. So let me use a comment. Get the train and test data, and we need to reshape them. Why do we need to reshape them? You can see that pizza has a shape of 512, 5123, but then if you run again, you can see that this image has a different shape. This is not good for the model. We want our model to see the images with one shape. So the images all have to have the same shape. They all have to have one unified shape, alright? Which is very good for the model training. So you have to reshape all the images to make sure that they all have the same shape. So to do that, I'll come down here and I'm going to import some few friends. So I'm going to import TF Keras, which is TensorFlow Keras, and I'm going to import TensorFlow itself as TF. Alright, so let's define the image shape. What is the shape we want all our images to have? So I say image shape equals, now I'm going to pass in 224, 224, and then we have to have a batch size. I will explain this one also later, and we'll see 32. So you probably might be asking yourself, Dennis, why did you choose 224, 224 as the image shape? Well, it turns out that the images for Imagenet, the images that were used for Imagenet, they all had this particular shape that we are using. They were trained on shapes of 224 and 224. That is one major reason why I decided to use 224, 224 as the image shape. Great. So now let's get the train data and let's get the test data. So at this point, we are going to do something called pre-processing. So when we talk about data pre-processing, they are the things that we do to our data before we feed the data into our AI model. Now remember that we have not created the AI model yet, but we have our data. So the things that we do to the data before we pass the data into the AI model is what we call the pre-processing. We already noticed that some of our images had varying shapes. So we have to pre-process the images so that we can have the same shapes for all of them. So let's start from the train data. So to get our train data is inside a directory. So we have to get it from the directory. So we are going to do something called, we create a variable train data equals. Now here is what TensorFlow comes in. If you go to TensorFlow, the documentation, And as you can see, if I search for this, let me clear, I searched for it earlier. We call it image dataset from directory. So I search for this. Now this tf.keras.preprocessing.image dataset from directory, what it does is that it is going to pull the images from our directory. So we have to give it the directory we want to get our data from, the labels, the label mode, the class names, and the others. So this is what is going to pull our images from our directory. So as we do it, you get to understand it better. So we said tf.keras.preprocessing, and then we said image data set from directory. We have it here. Then there were some, we need to pass in the directory. So where do we get our train data from? We get our train data from the train directory. So we pass in train directory. Next up is the labels. So our labels inferred, yes, they are inferred. I'll explain that as we go along. So labels, we give it equals inferred. I'll explain that as we go along. The next one is label mode. So label mode, we are going to pass that categorical. The next one is class names. So class names, we also pass that one to be class names. Remember, we already have our class names at the top here. We already found the class names here. The next thing we look for is color mode. We can pass that, but remember we have batch size. So let's do the batch. The color size is 3. You can see this is here we have 3. There is RGB. It's a 3 color, has 3 color channels. So there's no need to use that. We can pass it. It's default. So we can pass the batch size here. And then we've already created a variable here for our batch size. So we can pass that in as batch size. Good. The next thing is image size. So I hope you are reading it from here also. Image size. That what we have here is the same as what we have here in the documentation. You see, we have the directory, labels, label mode, class names. It's the same thing we are also seeing from the pop-up here. So we move to the next one, which is image size. The image size, we have a default value of 256, but remember we already have what we want to pass in as image shape. So we say image shape. Good. The next thing we have is shuffle. Do you want them to be shuffled? Yes. So we can pass shuffle equals true. What else do we have? We have seed, validation, interpolation. Okay, we can pass the rest, so we can leave it to that. So now let's explain what we have here. So let's use the documentation. If you go to documentation, it says that if you want to use this tf.keras.preprocessing.image dataset from directory, your directory should be in this format. You have a main directory, your class name, so class A, and then a bunch of images, then class B and a bunch of images. If you come here to our directory, you can see that is exactly what we have. We have this here. So for the train that we are doing currently, we have class A, which is chicken curry, and then when we open chicken curry, we have a bunch of images. If you go to another class here, chicken wings, this is the name of the class and then a bunch of images. So you can see that we are actually following what the documentation says, given the directory structure. If you move along the directory, you see directory where the data is located. If labels is inferred, it should contain subdirectories, each containing images for a class. Otherwise, directory structure is ignored. This is why we are using the inferred. You can see that these are our labels. This name here, chicken curry, is our class name, is our label. So it's actually following what the documentation said. So that's why we're saying that the labels are inferred. So if we want to know the label here, TensorFlow is going to name this as 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 9. So TensorFlow is going to infer that each directory, each subdirectory is a class. Each subdirectory here is a class. That's why we say the labels are inferred. Then next we say label mode. String describing the encoding of labels. Options are, we have int and then categorical. So categorical means that the labels are encoded as a categorical vector. Example, categorical cross entropy loss. So our labels here are categorical because they are going to be 0, 1, 2, 3, 4, 5, 6. So they are going to be 0, 1, 2, 3, 4, 5. If they were one hot encoded, then we are not going to use categorical. So some of these things you have to do extra research to properly understand them. So for the categorical, it means that we are going to use actual values for the class names 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So yeah, that is a categorical vector 0, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so they will use that as our class names. Then for the class names, you already found that only valid if labels is inferred. We already know that our labels are inferred, right? This is the explicit list of class names. We know we have the list of our class names already. If you go up, it's an explicit list of all our class names, and it goes according to the structure we have over here. And the next up is the color mode. We know we have RGB is the default value. We have 3 color channels. The batch size, the default is what? 32, which is what we passed in. Then for the image size, the default is 256, but we decided to use 224. Then order to shuffle the data. So anytime we pick the data to feed into our model, we want to shuffle the data before we pick 32. We feed it into our model. We shuffle the data. We pick 32. We feed it into our model. We shuffle the data. We pick 32 and we feed it into our model for the training to continue. Now this is optional. Seed is optional. I think the rest, majority of them are optional, and some of them have default values, so you could take some time to read them. So we have our trained data, and we have it pre-processed according to this batch size and this image. So let's do some printing. Let's say print, then F, and say training data. Great. So we can do the same thing for our test data. So I can just copy this here and then make some subtle changes to it. So this is going to be our test data. The directory here is going to be our test directory. If you are wondering where this test directory or this train data directory is from, remember we already created them up here, train and test, so that we can get the data from those directories. So from directory, we are pulling the information from these directories to create our test. Then again, the labels are inferred, categorical, class name, batch size, image size, shuffle equals true. The same thing we have over there. So we can also type here and say test or testing data. And just do the same thing here. Great. So if you remember what I said, we said we are taking the images. There are a lot of images, but we are taking them in batches. We take 32 of the images and then we train our model on it. We take 32 of our images and we train our model on that. But then to make our model perform very well, there is something that can actually help with the picking of or fetching of the images and then feeding into our model. There is this thing called auto-tune, so we can add it. So what is auto-tune is that I'm going to type it out and then afterwards I'll explain. So you see, for performance reasons, we are going to say auto-tune. Let me use caps here. Is it going to come? Yeah, okay. So tf.data.auto-tune. Wonderful. So we say train data equals train data.prefetch, and we give it a buffer buffer size. Did I make a mistake somewhere? Okay, let's see it again. Auto tune train data dot prefetch buffer size, okay, equals auto tune. Wonderful. I can just copy this and paste it one more time. Nope. Now we use this for our test data. The same thing, test data. So what this means is that, or what we are trying to do is that, instead of picking 32 images, then feed it into the model, and then we have to wait for the model to work on that, and then we have to wait to fetch another 32 and then feed it into the model. What this auto-tune prefetch does is that it prefetches 32 images. So while your model is training on 32 images, we will prefetch, so you don't have to wait. We will prefetch 32 images so that the moment you are done with training on the 32 images, the next 32 images also gets fed into the model. So once you are done training on the 32, you don't have to wait to go and take the 32 and now feed it into the model. So it's like you always have 32 images ready to be fed into the model. So this is what this here does. It always makes sure that you have your images prefetched. They are always ready to be fed into your model, so that you don't have to be waiting to finish training and come back for 32, finish training and come back for 32. You always have 32 images ready to be fed into the model. So that's why it's just for performance reasons. So let's run this and see. We might have some errors. We may fix that. Oh, great, no errors. So for our training data, we have 750 files belonging to 10 classes. So the total number of images we are training on are 750, and they all belong to 10 classes. Then for our testing data, we have 2,500 images belonging to 10 classes. So this is the total number of images we are training our model on. And this is the total number of images we'll be testing the model to see how well it performs. You see, it's just like an exam. Before you write an exam, you take a mock. You train yourself on the exam, and after you train yourself, you take the exam itself to test or to evaluate how well you have learned. So it's the same thing. You train the model on these number of images, and afterwards you test it on this number to see how well it performs. So you can see that in this case, we have lots of testing images and very little training data. This is particularly on purpose. It's intentional. We just want to see the power of feature extraction. Wonderful. So next we can go ahead and actually create a model. Before we go to creating the model, let's do something here. Let's go back to EfficientNet and read a little about EfficientNet. We said we are going to do feature extraction. So if you take some time to read through the docs here, so we have TensorFlow 2 classification. So we are not doing classification, we are doing feature extraction. So we have to change this to feature vector. Wonderful. Okay, and then we have some sample code on how to go about it. So we have to import TensorFlow hub as hub, mtf.keras sequential, then hub.keras layer. Then this is the link to EfficientNet. Trainable equals false. Then we have a dense layer. Okay, let's check for ResNet as well. Classification, no, we want feature extraction. Then the same thing, let's see an example of it. Okay, there's an example of how to implement it, just like we had for the other. So instead of downloading the entire ResNet from here, we can actually just use the links provided here and implement them in our model. I think the same thing goes for EfficientNet. We can just pick the links from here and then implement them in our model. So I think we need to actually try and understand what feature extraction actually is. So I'll try explaining it verbally, and afterwards I'll show you a picture of how it actually works. So what we are doing is that these models that we have here, they've been trained on Imagenet on a large class So you can see that it's saying that if you look at the example we have here, it says that trainable equals false. It means that the EfficientNet, when we are doing feature extraction, we do not want to train the EfficientNet. We don't want to train EfficientNet. But what we are going to train is on the last layer. And on this last layer is where we are going to indicate the number of classes. So we have to fix in our number of classes. In our case, we have 10. So it's giving us the flexibility to remove the head. So this EfficientNet has a natural head of over 1,000 classes. But if you want to do feature extraction, what we are going to do is that we're going to remove that head and fix our own head, which is the number of classes on top of it, so that it can now classify on the classes of images that we want it to classify on. So take away the head, freeze the EfficientNet itself, attach your own layer, and then fix your number of classes so that you can use the EfficientNet to classify your images depending on your number of classes. So we freeze it, we add our own layer, and then we force the EfficientNet to classify based on our number of classes. So that is what we are doing with the EfficientNet. The same thing with the ResNet. We say freeze the ResNet itself. We are going to add our own layer, then we add our own number of classes, in our case which is 10, so that we can force the ResNet to make predictions based on the number of classes that we are going to give it. So that is what feature extraction is basically about. You are going to freeze the layer, you're going to freeze the model, and then attach your own output layer and indicate your number of classes with your activation function. So it's pretty straightforward and not too complicated. So before we go in there, I want to add something called Tensorboard. So on TensorFlow, we have something called Tensorboard. If I search for it here, so this Tensorboard, what it does is that it helps you to visualize, as you can see there, visualizing metrics such as loss and accuracy. So as our model, we are about to create our model. So after we create a model, we want to be able to visualize how well our model is doing. As you can see, some lines, some graphs over here, the ability for us to visualize and say that, oh, our model is doing very well, our model is overfitting, or this or that or that. This Tensorboard actually helps us to visualize all of that. But again, Matplotlib also allows us to do this. But using Tensorboard is quite the professional way of doing this. So actually, we are going to use both to do the visualization. So I'm going to go back here and let's first create the callback for Tensorboard, and afterwards we can create the model. So to do that, we can start by saying creating a callback function for plotting loss and accuracy curves. So how do we actually create a Tensorboard? Let's do this way. So we can do Tensorboard callback, and we say that tf keras dot callbacks. Then let's see whether it shows up. Tensorboard, great, it shows up over here. So Tensorboard. Now, what argument does it take? It takes it takes the argument of the log directory. So what is the log directory? So let's see. Log directory equals. So what should our log directory be? So one perfect way of doing that is that let's go to the top here and deal with the log directory and then assign it. So we come log directory equals OS, depending on the system you're using, path.join. We're going to pass in, we're going to have the name of the directory, the experiment name, and then we do some gymnastics here. Datetime dot now Now this is all in the documentation. So in case you don't understand something, you'll find everything I'll show you later on. Everything here we have is in the documentation. So we're going to say that this directory name here is going to be a string. The experiment name is going to be a string. Then we have the date time. Now we are going to stringify it. We're going to turn it into a string. So we start with the year, then we add the month, and again we add the day, so D, and then we add the hour, which is capital H, we add M, which is the minute, and then the second. So this is how we actually stringify this date time. I'll explain as you go along, so no need to worry now. And I can pass this log directory here. So the best way, or the best thing to do right now, is that we can create a function, because we have not defined this directory name, the experiment name. So we can do def create Tensorboard callback, and then the user has to pass in the name of the directory, the experiment name. Yeah, that's enough. And then we can push everything here into our function, just like that. Wonderful. So what we are doing here is that we are joining the directory name, the experiment name, and then the date time. We are joining all of them together as a string, because we will stringify this, and then we get a string of the path. Then we do the keras callbacks, and then pass this log directory to this log directory. Don't worry if you don't understand this right now. When we get there, you clearly understand what we are trying to do. So I'll say return the Tensorboard callback. So this function is going to do a lot for us here. Great. So what else should we do? We now have the function for the Tensorboard we are talking about here. And a lot of the code that I wrote there, you can find some of them in here. It's very, very simple. If you take some time to go through it, so you can see some of the log directory, the code that I just wrote, you can see a similar one here, datetime.datetime.now.stringify. So majority of the code that I'm writing, you can clearly find them in the documentation. So let's go back here and continue. So now we can go ahead and then create some models. So let's run it to make sure it is working properly. Great. And then now we can create a function for our models. So let's say now we can create a function also for our model. Now, why do we need a function to create our model? Remember that we are dealing with two models, right? So if you're supposed to do it one model after the other, we have to keep doing the same thing twice. But with a function, once you create one function, you can create multiple models without rewriting the entire code. As you go along, you will understand clearly. So let me say I'll create another function called create model. Remember that we have our data prepared, but we don't have our model created. So we are going to, let's check some stuff here. We are going to create a feature extractor layer, and then use exactly what was in the documentation. If you come back here, it says that import TensorFlow hub as TF, then do TF keras sequential hub.keras layer, this kind of stuff here. So we're going to do the exact same thing. So I'll go back here, and then I have to import what it asks me to import, which is TensorFlow hub. And then I'll do exactly what it did. Hub.keras layer. Great. Now we go back here and see in the hub.keras layer, the first thing here is a string of a link, right? And then trainable equals false. Then we have something also here. So how do we turn this into a function? we need a URL here. So let's go back there and say we need a model URL, that is a link to it, and then trainable equals false, and let's give it a name. This was not part of the argument, but let's just give it a name and call it feature extractor layer. Oh great. So we don't have the model URL right now. So when you are creating a model, we want the user to pass in this model URL, right? So I can just come here and add model URL. Great. Now if you go back to the documentation here for on Kaggle, everything here was inside a tf.keras, right? So that means that we have to put what we created, this here, inside a tf.keras.sequential. So let's go back in there and continue with that. So the first thing we are going to do is that we already have this layer here for ourselves. So we're going to create a model itself. So we come down here and say model equals now tf keras.sequential. Now in here for the sequential, we are going to do something. We want an input layer. So I'll do tf keras.input, and then I'll indicate the shape. I'll explain this as you go along. We want the image shape that we said before. Then we want to add the color channels to it. Yeah, and then the next thing we want to do is we want to do another pre-processing. Keras.layers. I'll explain this as you go along, so don't worry if you don't understand it right now. And then we have 255. Great. Then now we can add our feature extractor layer. Great. Then we can add the last layer inside the documentation, this layer, which is our layer. This is what makes feature extraction important. This layer is the most important. So we come back here and then we say tf.layers.dense. What is our number of classes? And then our activation, you say relu. No, activation is softmax. Now the number of classes has not been defined, so we can come to the top here and say number of classes. This will make this function reusable, so we don't have to write this code every time. So we can do a length of class names. You know we have the class names, so the length of the class names is going to be 10. We have, if you go back to the top, this is class names. Its length, the number of classes we have is 10. So we are passing in that number of classes here as 10, and then the activation softmax. Now if it's a function, then you have to return something. So return model. Let's go back and check things to see that everything is correct. So we have our softmax, number of classes, trainable, and the model URL. So because this, what we have here is the same as what we have here in ResNet, all we have to do is to just pick this link and then we are good to go, because we have a function that we can reuse every time. We just have to know the model URL, just put it inside, and then we are good to go, because you can see that they are all the same. The only difference is this URL we have here, and the same thing, the only difference is this URL. We are using the same number of classes, which is going to be 10. So we just have to get the module URL, put it inside, and then we'll be good to go. So let me explain more about what we are doing here right now, and then let's make some few changes. So this keras layer that we are adding, if you are familiar with TensorFlow and then building sequential models, this feature extraction layer is from keras layer, but then the only acceptable layers that are supposed to be in sequential are supposed to be this kind of layers, dot layers. You can see this layers is different from this layer. They are two different layers. So you can see that I am not using what is over here. over here it is tf.keras, but over here I'm using t-keras. So we are going to go back and then ensure that anywhere we use keras, we use tf-keras. So with the names here, we use the training tf-keras, and then here to tf-keras. The reason why we're using tf-keras is that for model compatibility, this keras layer is different from these layers. So if you use tf.keras, you're going to get an error. So I have to make these layers compatible with this different kind of layer by using tf-keras. I've actually run into this error before. That is why I know it before getting here. And then the image shape, we had 224-224-3. So we are adding this to it. So what this here is, it actually looks like this. Something like this. 224, and then we added 3 to it. So this 3 here is a tuple. That's why there's a comma after the 3. So add this 3 to this, what we already had, the image shape. If you remember image shape, this is image shape, and we are just adding a 3 to it. So the height, the width, and the color channels. Yeah, so the height, the width, and the color channels, that's what we have over here. And then we are doing some rescaling here. So this rescaling is also part of the pre-processing. If you look at the images that we have, they are of this type, 512509, and the images are within the range of 0 to 255 pixels. Naturally, images are within the range of 0 to 255 pixels. But in AI, the models perform best when the image pixels are between 0 and 1. So that is why we are dividing the images. Over here, we are dividing the images by the highest pixel, which is 255, so that we can have the values between 0 and 255. So when you go to documentation and you type layers.rescaling to read more about it, so we have the scale value here, and it says that to rescale an input in the 0255 range, the images we have in our dataset are all within this range, 0255. Now we want to reshape it to 0 to 1 into this range, because this is what our model performs best. If we are doing any AI using images, they will always perform best when they are pre-processed from this to this. So we are changing their pixel values from this to 0255 to this value here, which is 0101, that range. To do that, this is how you do it. You pass the scale value here. The argument here is scale. So the scale value is supposed to be 1 point divided by 255, which will put it within this range. There are other scaling values here, but we are more interested in this one. So that is why we are doing this over here. Again, you can also search about the sequential in the documentation to read more about how we generated this. Wonderful. So what is there again to talk about? So we have added the feature extractor layer, and we've added our output layer. So let me add some comments here. Let's say input layer and rescaling layer. Perfect. Now here we have the feature extraction layer. Okay, so we are feeding this image into the model. It's an input layer. You feed it into the model. This is our model. We feed this image into the model. We rescale it to make the pixel values between 0 and 1. Then it goes through this feature extractor layer, depending on the model we are using. Then we have our number of classes here to be 10, and then we have our model, and then we can go ahead, compile, and make some predictions. So we have this here working properly. Is there anything else we have to do? I don't think so. So let's run to see. Great. So we can go ahead now. I told you before that for the visualization, we use Tensorboard. But then there is also another way we can use using Matplotlib. But I think we should hold up to that one for now. And then continue with this and then come back to that. So there is a framework that I use whenever I'm coding these things up, that I give numbers to it. It's like 1, create the model, 2, compile the model, 3, fit the model, and then 4, evaluate the model. So first we have created the model, right? We have created a function for the model. So let's get some model URLs so that we can compile the model. So I'm going to put it here so that in case you're also learning machine learning, to always be at the top of your mind. So we have this one, create the model. Or let me just clear it. We can come back to it. So let me just come here and say model URLs. So what's the URLs you want to get? You want to get ResNet URL equals. So let's go to ResNet. Here is ResNet. Make sure it is at feature vector. And then we're going to pick this here, the string URL here, copy it, and then put it in here. Beautiful. Then next we want the EfficientNet. EfficientNet URL. So we can go to EfficientNet and copy its URL. Again, make sure it's the feature vector. Feature vector, correct. So we can come back here and then paste it. Beautiful. So we can run it also to make sure everything is perfectly. Great. So now we can start creating the model. So let's say 1, create a model. So how do we create a model? Let's start with ResNet. ResNet model. How do we create a model? Remember, we have a function for creating the model. So you can go to create model. We can call the function, make an instance of it, and then pass in the model URL. What should the model URL be? We already have the model URL. So you can say ResNet URL, right? And that is all we need. We don't even have to pass in the number of classes because you have a default value for it. Okay. So now we can actually run this. The next thing to do is to compile the model. I told you there are 4 steps. 2 is compile the model. So how do you compile the model? You go to ResNet model.compile. You say loss equals categorical cross entropy. Optimizer equals Adam. So Adam, you can say tf keras dot optimizers dot Adam. Okay, that looks a little long. You see metrics accuracy. Yeah, so what are we doing here? We first created a model. Now we are compiling the model. When we say we are compiling the model, if you go back to the documentation here and I type sequential, so you can see we have different forms of the sequential model here. Layers.dense, and blah 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 here. And then let me go back and search for this rather, tf.keras.sequential, so that we can see the other functions for it. Great. So this sequential, Keras the sequential that we use to create the model, it has additional methods called compile. You see, it has another method called fit. So it has another one called predict. It has another one called evaluate. Where is it? We have evaluate. So it has different methods under it. What we are doing right now is the compile. So with the compile, you pass in an optimizer, you pass in a loss, and you pass in some other values, the metrics. Mostly these 3 are enough. So that is what we are doing over here. So you come to the compile, we have our loss, categorical cross entropy. Remember that where our class labels are categorical. If you remember from the directory, when we were pulling it from the directory, we said they are categorical. They are 0, 1, 2, 3, 4, 5, 6, 7, like that. So categorical. So this loss, what it does is that whenever the model makes a mistake, it tells us how the model should correct its errors, or it tells us how wrong our model is. So to compare, the loss actually just computes how wrong the model is. Then we have the optimizer. What the optimizer does is that it uses the loss to improve our model, how to optimize our model or how to improve the model. Then the metrics accuracy is how we measure our model. So we measure our model by how accurate it is. And then we optimize our model with the Adam optimizer to improve it. And then the loss will compute for how wrong our model is so that we can optimize it using this optimizer. And then we are measuring it based on its accuracy. So I told you we have four things: create the model, compile the model, fit the model, and evaluate the model. We have done two of them, so let's move to the next one. So the next one is fit the model. If you remember from what I showed you here, the sequential has several methods. We have compile, we have fit, right? So right now what we are doing now is fit the model. So X, Y, batch size, epoch, variables, validation, shuffle, steps per epoch, validation steps. So this is what we are going to do now for the fit. So this is, let's get it done and then I'll explain it. So we are going to do ResNet history. I'll explain this one also. So you say ResNet model.fit. Now what are we fitting it on? On the train data. We pass in the epoch or the number of epochs to be 5. Then steps. Those are this time our pop-up is not showing. To do that, you can do shift. Okay, it's now here. We have steps. Where is the steps? Steps per epoch. That is over here. Steps per epoch. So we can just do this. And the steps per epoch, we can do the length of the train data. Great. The next one, we can go ahead and then look for the validation data. So validation data, that will be the test data to validate our model. Then we can go ahead and do the validation steps. So you can always be using what you have on top here, or you can go to the documentation and then check it from here. So we are using validation steps here. So validation steps will be the length of the test data. Great. What we can add here is the callback. We created a callback, if you remember. So if you go back here and check, do we have callbacks? Yes, we have callbacks here. And this callback, you see, it's callbacks. So it means that it can be plural. We can have a lot of callbacks. So it takes in a list and we can use a callback in there. So let's do something here. So we take a list here. And then remember we made a callback for the Tensorboard. The Tensorboard callback. This Tensorboard callback here. tf keras.callbacks Tensorboard. Right? So we are going to use this in our callbacks so that we can create a directory, the experiment name, to store the results of, or the history after the training of our model. It gets clearer along the way. So let's go to create Tensorboard callback. We have it here, and then we have to pass in, I think, two arguments: the directory name and the experiment name. So the experiment name, we can pass in a string, of course, as the directory name to be TensorFlow Hub. You can name it anything. I choose to make it this name as my directory name. And then we say ResNet 50 version 1 Great. Yeah, so we added our callback. Let me add here, add the Tensorboard callback we created earlier. So this is going to create a directory inside our project that is going to store the results over here. So this history that we have over here, this history will store the results of the training. It gets clearer as you move along. All right. So we can start the model training. This is going to take some time, so I think I might pause the video and come back to it. So let's try and see in case there are any errors before I leave it. So let's try. Let's run it. Oh, good. So it says that model.fit got an unexpected keyword argument callback. So you can see that I made a grammatical error here. It's supposed to be callbacks. And we can confirm it over here that the name here is callbacks. So I come back here and fix it to be callbacks. Validation steps, validation data, steps per epoch, epochs 5. So I didn't explain epochs. Epochs is the number of times you train the model, or the number of times you go through the image data set. So we want to train it for a very, very small period of time. As you go along, you understand more of these things. But I think we have no error, so I'll run it again. All good. So now it starts. We are training our model for only 5 epochs on our trained data set. So what model.fit means is that we have created a model. You can see it's running very fast because we are using a GPU. So what model.fit means is that we have created a model and then we have trained data. Now use the model that we have created, which is ResNet model. Use that model to find patterns inside this trained data. Okay, and then we are measuring it by accuracy. We want to see how accurate this model is in fitting or in finding patterns inside this trained data. And then we are also going to validate as it is finding patterns in this trained data. We also be testing the model to see how well it is performing along the way. So as it is training, we are also testing it. We are evaluating it to see how well it is performing as it trains. Okay, that's why we pass in the test data as for validation. You want to validate. Okay, you want to test it to see. So it's working for only 5 epochs and it should be done very soon. Wonderful. So it is done. So let's see how well it performed. Oh wow. So we have the training. This here is loss. This loss is training loss. And this is training accuracy. Okay. So the training loss is 0.3. That is 3%. And then the accuracy is 92% on the training. But remember, the training here doesn't really matter. What really matters is how well it performed on the test data. That's data that it has never seen before. This one we just use it for training. But then how well it performs on the test data is the one that is very, very important. So when we check, you can see that the validation accuracy is 82. So it means that its accuracy is 82%. That is the most important thing. Then its loss is around 0.556, which can be improved if you decided to train for like 10 epochs or more. So this is how well the ResNet did on the trained data. Its accuracy was 0.82. So we can actually go ahead and then see how EfficientNet will also perform. Okay, and then we can now compare the two of them. So to do that, let's create a model. Because you have already created a function for the models, it's going to be very easy for us to create a model. So now we do EfficientNet. And as always, the first thing is what? Create a model. So we create a model called EfficientNet. And we have a function that we can create an instance of create model. And then all we have to pass in is the EfficientNet URL. Remember, we already have the EfficientNet URL. EfficientNet URL here from Kaggle. We have it from Kaggle. So we come here and then we can pass in the EfficientNet URL. Great. So now we can actually run this to ensure that we have created a model called EfficientNet model. The next thing we can do is to compile the model. So to compile the model. So how do we compile the model? You say EfficientNet model dot compile loss equals categorical cross entropy. This one measures how wrong our model is. Then the optimizer is Adam. So you can have tf keras.optimizers dot Adam. Now remember that this whole long thing that you can actually make it very simple by just doing this Adam. But I choose to write the entire thing. Let me clear it up. You can just do it just like the way we have this categorical cross entropy. You can also type it this way as tf keras dot losses dot categorical cross entropy and do this. So this thing that I've written here, categorical cross entropy, you can also write it this way, right? Like the way I have it here. But then it's all up to you. So we have Adam. Then the next thing you can do is the metrics. So metrics is plural, meaning we can measure different things like F1 score. There are a lot of them, about 4 I know of. The area under the curve, F1 score, precision, recall. But here we are just using accuracy. Great. So the next thing we can do is to fit the model. So 3, fit the model. So EfficientNet model history dot fit. So how do we fit it? We have the train data. So you can copy from before, or you can just type everything out. We said 5 epochs, steps per epoch is equal to length of the train data. We can talk about the validation data for the testing. Test data. Validation steps equals length of the test data. And then the callback. Create Tensorboard callback. Then we have to pass in the name of the folder. So we said TensorFlow Hub. And then we have to pass in the experiment name. Now remember that this experiment name is different. The first one was for ResNet, but this one is EfficientNet. But it's the same directory, but different experiment. So we have EfficientNet v1 or version 1. So here we had TensorFlow, and then we have EfficientNet v1. Here we had TensorFlow Hub by ResNet. The experiment name is different. Remember, we created this Tensorboard on top as a callback. So we can now train this to also see. So let's train it. Okay, so started with an accuracy of 0.4 and a loss of 1.8. So let's see how this one also perform. You remember I talked about the fact that for the visualization, we can also do it with plot loss curves, or we can use it with Matplotlib. So we can use Matplotlib to do the visualizations. You know, these numbers you see on the screen, not everybody can actually understand and read them. But then if you're able to plot it, it's easier for everybody to be able to visualize what is being communicated. So the next thing we're going to do after here is to, make a plot of these results so that it will be easier for anyone to understand. So you say plot the model. But then let's check something here. Wow. You can see EfficientNet actually has a, a training accuracy of 0.9, but look at the validation accuracy is 0.86. So you can see that its accuracy is higher than the accuracy of ResNet. Wow. So you can see that it is doing it. EfficientNet outperformed ResNet in terms of the accuracy. It actually outperformed it, but by a slight margin, by a very important margin, 0.82 and 0.86. Wow. But then let's focus on the plot now. Let's plot it. So again, we can create a function here and say plot loss curves. So I said we are going to plot this information here, but how do we get this information here? You see, this information we have over here, how do we get them? Remember that we store them here in something called history, right? This one also has history, so we can pass in their histories, and then we'll be good to go. So what are we going to do? We're going to use matplotlib again. So plt dot figure. Let's define the size of the figure, like the graph we are going to plot. We want the size of it. I think my spelling for size is wrong. Yeah, size. And then let's use 12. This one is, you can pass in any value. I just like using 12 and 7. And the next up, we don't want them to be too close, so we want a tight layout. You can actually skip this one. The next one to do is that we want two plots, one for the loss. We want one plot that will tell us this loss, the training loss and the validation loss, and another one plot that will tell us the training accuracy and the validation accuracy, right? So we want two plots. So you have to make two plots, we have to make something we call a subplot. So plt.subplot, we want one column or one row with two columns, and then this plot is going to take the first position in that column. When we visualize it, you actually see it properly. So we say plt.plot. Now what are we plotting? We are plotting the history. So history, whatever history we put in there, dot history. Where from this history, this variable here, or this fit model here, it returns a history. So when we say history, that is the history we are trying to get. It actually returns a dictionary of, or an object of a history. So whatever history we pass in, the history of it, you understand it more because it returns a history. So we take the history and then we pass in a loss. We can give it a label and say something like training loss. Training loss is fine. That's for the training loss. And I think I will just copy here, come down and paste it, and then change this one to var loss. It doesn't hit. And then this one to, I'll just change it to validation loss. Most of these things, if you haven't done it before, when you are doing the visualization, it gets clearer. Then I want to give it a title. So plt.title, which is a string, I'll say loss, because the two of them are all losses. One is for the training and one is for the validation. Then for the x-axis, px label, I'm going to say epoch. That's the number of epochs that will run on the x-axis. Then plt.legend, so that I'll be able to know which graph, like which line is which line, or whenever you will understand it when I plot it. This legend here will enable us to know that when this loss line that will be on the graph, it is training loss. Also, you can color it to be, let's say, red, so that we label it as training loss, and then we color this as blue and say that is validation loss. That is what this label is doing here. It connects to this legend. All right, so we can do the second one. Instead of typing everything out, I'll just copy everything and then repaste it. So I told you that this subplot means that we have one row, two columns, and then we are taking the first column on the row. So if this plot took the first column on the row, this should take the second column on the row. So we can change this to 2, right? And then this one was loss, but in this case we are doing accuracy. So you can see accuracy, right? Just as we have over here, we have var loss accuracy, loss var accuracy. So I can change this also to training accuracy for the label. And again, var loss, I'm going to change this to var accuracy. Then the validation, I'm going to make it validation accuracy. Okay, this time I didn't type it T. Then the title is going to be accuracy. Then yes, the x-axis is also going to be the same thing. And I can do here as plt.show. I'm adding this because if you remember when we used plt before, there were some numbers written on top of the graph that we were not interested in. If you want to get rid of that, you use the semicolon. Okay, so I think now if there are no errors in this, if there are errors, we'll come back and correct them. If there are no errors in this, we can actually use them to do the plotting. So which of them should we plot first? Yeah, which of them should we plot first? We can first plot the loss curves for the ResNet. Okay, so we can say plot the loss curves. So let's say plot, no, not plt, plot actually. We want to use the function plot loss curves. Then we pass in the history. Which history? This history, right? So for ResNet will be somewhere here. ResNet history. And we put it in there, right? And then we run it. Wonderful, wonderful, wonderful. So this one, you can see the number of epochs down here from 0 to, we run it for 5 epochs. So I mean, it continues. Real wonderful. And then this, the line blue is for the trailing loss. You remember when I was telling you the label, the color is blue, so that means the blue line is for the training loss. The label validation, the orange one, is for validation. And the same thing goes for the accuracy. Wonderful, wonderful. So this one is for the ResNet. Okay, we can do the same thing also for EfficientNet. So we can say plots, not plt, plots loss curves, and we can go get EfficientNet as well and plot it. Wonderful. So this is for EfficientNet, and the other one is for ResNet. So you can see all of them. You can see EfficientNet's validation is a little bit higher than that. I mean, you can't really see it, but you can see it's a little bit higher, going towards 0.9 than the accuracy of this. The accuracy of ResNet. You see, the accuracy of ResNet is way below 0.9. So you can see the EfficientNet's validation accuracy is doing quite well. Then for the loss for EfficientNet, well, you can see it is the loss is really going down. It's really going down. For the validation loss, it kind of picked up. It was coming up a little, but well, it's still performing very well. But for the ResNet, the validation loss, you could see that the validation loss was kind of going upwards from here. There's some gap coming in here. So in my opinion, I'll just say that EfficientNet actually beats. I mean, the name is efficient, so I'm not even surprised. The EfficientNet actually performs well than the ResNet based on these graphs. So is that all? No. Let's do some summaries. Let's do some summaries here. So let's go down and look at the summary of our models. So let's start with the summary of ResNet. So not summary. I don't know why I keep typing T. Summary of ResNet model. So if you want to do the summary, you just do ResNet model.summary. Wonderful. And let's do the same thing for EfficientNet. So summary of EfficientNet model. So EfficientNet model dot summary, plunging in there. Nice. So you can see that we rescale them after we had the inputs of 224. So that's 0 parameters because there were no layers in there. Then we had the feature extractor layer with quite a huge number of parameters, almost 23 million parameters. Look at the total number of parameters for ResNet, 23 million. Now if you look at EfficientNet, how many number of parameters? Around 4 million. So you can see that EfficientNet is very efficient. It uses lesser number of parameters and it still performs better than ResNet. Even though ResNet is using 23 million parameters, EfficientNet is using only 4 million and is performing very well. One thing I have not talked about is the callback that we used. I told you that what we have done over here using Matplotlib, we use professionally, you want to use what we call the Tensorboard, which we use the callback for in our model. So if you go back to it, I just want to show you. We had a callbacks and then we said TensorFlow Hub EfficientNet v1. So it means that we should expect that in our project there is a directory called TensorFlow Hub inside our project. So let's go here and let's find out. Let's close these guys here. Oh, wonderful. So it looks like we have the TensorFlow Hub in here. Oh, great. So we have the directory name called TensorFlow Hub. It was the same thing for EfficientNet and the same thing for ResNet. So we should expect the experiment name for both ResNet, which is ResNet 50, and EfficientNet, which is EfficientNet v1, to be all inside this TensorFlow Hub. So let's open it and see. Oh, wonderful. So we have these two experiments inside our TensorFlow Hub, which is amazing. Now let's open it and see. So what we're expecting is that this EfficientNet and then ResNet experiment should contain what we call an event. And these events are what is going to enable us to view the results of our model in Tensorboard. So let's go back. Did it open? Okay, no. Let's go back and then do that. To open the Tensorboard, we can actually open Tensorboard right here without going to the Tensorboard official. Type Tensorboard. We can do this visualization right inside our Google Colab without doing it over here. So to do that, there are some very simple commands we can do. So first of all, you have to load the extension Tensorboard, right? And then you have to point this Tensorboard to where the directory is, where these directories are. You see, you have to point to where these directories are inside this directory, because it needs the event. It's going to search for an event in both of these in order to plot the Tensorboard. So let's do that. So first of all, we need to load the Tensorboard notebook extension. And then how do we load it? You saw it from the documentation. So load extension. What's the name of the extension? Tensorboard. Great. Now after you load it, you want to point the Tensorboard to where the log directory is. So you can do this and say Tensorboard. This is not capitalized, it's T and a B. So now point the Tensorboard to where the TensorFlow Hub directory that we created, where the Tensorboard is lying. Point it to that directory. So you say log, which is log directory, and then we pass in TensorFlow. How did we name it? TensorFlow Hub, right? Great. So this is how we name it. So first we load the extension like this. We load it, and then we point it to where it's located. You're supposed to have an example somewhere here. Great. So afterwards you point it on the command line, run the same command without this. So you do this, start Tensorboard through the command line or within a notebook experience. So you point it to where it is. Here, DS is logs fit. Ours is different. So you can take some time to read through the documentation. Everything you need is actually here. So we come back here and then we run the cell to see if you can have it. It takes a while to load, so you just have to be patient. Oh, wonderful. Wonderful. So if you look here, we have loaded our Tensorboard, which is inside TensorFlow. We loaded it beautifully, as like this. We loaded it beautifully inside our Colab, and then we can just go through it. So let me close this here, close that here. So what do we have? We have accuracy loss, then we have the evaluation accuracies, and then we also have the evaluation loss. Evaluation accuracy is the same as the validation accuracy and the validation loss. So this is training accuracy, training loss, validation accuracy, and validation loss. So let's look at the training accuracy. Wonderful. So you can see the same values we had, 0.89. If you go back to our, go back to our training, 0.89 for EfficientNet. 0.89, right? The same thing we have over here. So it's just plotting all that data for us. So you have our values for the training for EfficientNet, and then the validation is 0.86. This is our validation accuracy. So accuracy for the training is this, and the validation, you can see the name validation and train. 0.9 for training, 0.6 for validation. Beautiful. Now we go to the loss. What values do we have? We have 0.5 for the training and 0.454 for the validation, for the training and validation. It's the same thing if you check from what we had. And then we have the evaluation to our values 0.86 and 0.82 for validation. This is for ResNet. So you have to be checking the names, ResNet and EfficientNet. So it is comparing these two. You can see that the validation for EfficientNet and ResNet, you can see that ResNet is way above, EfficientNet is way above ResNet when it comes to the accuracy. Its accuracy is 0.6 and this one's accuracy is 0.2. You can check the validation loss for the two of them also. You can see that EfficientNet, EfficientNet also has a lower loss than ResNet, 0.54. So you can see EfficientNet is actually doing very well. Doing very, very well. Wonderful. So this basically brings us to the end of this project. I'm going to make all the resources to this available in the description area. I'll put a link to my GitHub. This notebook will be available on my GitHub, so I'll put the link down in the description. If you found this video useful, be kind to leave a comment, like, and make sure you subscribe. I'm going to be releasing more content the more I learn. So what we actually wanted to accomplish in this video was to compare two AI models, ResNet and EfficientNet, which have already been trained on Imagenet, to see how well they will perform on this Food101 dataset. Now, if you want access to this paper also, I'll link the link in the description. It is a research paper that was done some few years ago. So the Food101 actually, they use random forest to train on this dataset, and they achieved an accuracy of 0.57%. No, 57% accuracy. But if you look at what we did over here, using feature extraction, we've been able to attain an accuracy of 86%. So we moved from 57%. The accuracy when they use random forest was 57%. And then when we use feature extraction, that is using pre-trained models, we've been able to attain an accuracy of 86%, which is significantly better than 57%. So you can see how good feature extraction actually is. Taking an already trained model and then fitting it onto a customized data set. So you pick a data set, pick an AI model that has already been pre-trained, and then use it on your data, which in this case actually significantly increase our validation accuracy. So this kindly brings us to the end. I'll leave the links to everything in the comments in the description section. Don't forget to like and subscribe, and then continue learning, and happy machine learning.